Okay, calculus and vectors class. So in this lesson, we're going to focus in a bit more on instantaneous rate of change and talk about how we can use that to help us get a bit more accurate information about problems that we might come across over the next little while. So before we do that, let's do a quick recall of what we talked about in the last lesson. We said the average rate of change between 2 points in time is found using the slope of the secant. And the instantaneous rate of change is found by the slope of the tangent at the given point. And we said finding a tangent is a little bit tricky. What we're going to do is we're going to sketch an approximation of the tangent passing through the point of interest, which I've shown in this diagram on the side. Then we're going to pick another point, which I've drawn off to the side on our graph, one that's off of the curve, and then we can calculate the slope. So at this point, that's the most accurate method that we have of figuring out the tangent, by just kind of guessing with our tangent and just doing a sketch. So obviously it's not super accurate. So over the course of this lesson, we're going to start finding more accurate methods to do that. So an estimate of the instantaneous rate of change can be found by sketching an approximation of the tangent at a point and finding its slope if it's a graph, or by calculating the average rate of change about the smallest interval for which data are available, if given a table of values or equation. So remember when we had an interval of 9 seconds, and then we measured for 6 seconds or 3 seconds, and we saw that the results kind of approached our instantaneous rate of change, but again, not super accurate. So to start trying to figure out how to get a more accurate instantaneous rate of change, let's start with a problem. Example 1, an outdoor hot tub holds 2,700 liters of water. When a valve at the bottom of the tub is opened, it takes 3 hours for the water to completely drain. The volume of water in the tub is modeled by the function v of t equals 112 times 180 minus t squared, where v is the volume of water in liters at time t in minutes. It's asking us to determine the instantaneous rate of change of the volume of water at 60 minutes. So at 60 minutes, that split second in time, how much water are we losing every second? So to do that, we're going to follow the same method that we did in the last lesson, but we're just going to start at 60 and use an interval that's a little bit further away, and we're just going to make those intervals smaller. So what that means is we're going to measure from 60, that's going to be to 63 minutes. Then that's 1 minute past, it's 61 minutes. Then 60.1, 60.01, 60.001. So essentially, we're just looking past to 60. We're just looking past 60 to smaller and smaller intervals, and we're going to see if we can start to see a pattern that emerges. So that means it's going to be 60.1, 60.01, 60.001. And all we're going to do is we're going to take those numbers there, 63, that number 1140.8, was just found by plugging it into the formula that which I've highlighted in orange. And you get that number, then 1180.1. If you do the same for 60.1, you get 1198.0. Then we get, for 60.01, we get 1199.8. And then we get 1199.98. So the last step, we have to find the slope of the secant. So this is just the slope of the tangent point P, tangent point Q. So we're just taking the difference in the y's, the difference in the x's. So for point 1, that was 1140.8 minus 1200 divided by 63 minus 60, and we get 19.7. For the second row, now we're going to do the difference in the y's, which is 1180.1 minus 1200 divided by 61 minus 60. And when you do that, you get negative 19.9. So we're not far off from the first one. We had negative 19.7 and negative 19.9. So that means over the first 3 minutes, we were losing an average of negative 19.7 liters per minute. If we just look over 1 minute, we're losing negative 19.9 liters in that minute. Now, don't get thrown by the fact that we're going less than a minute. We're just kind of trying to figure out in that tenth of a second, if we were to extrapolate, what's going to happen. So for this one, we're going to do the same thing. We'll calculate the slope, 1198.0 minus 1200 divided by 60.1 minus 60. And that's going to be negative 20.0. Let's repeat the same thing for the fourth row. That's going to be 1199.8 minus 1200 divided by 60.01 minus 60. Punch that in your calculators and you get negative 20.0. And lastly, we have 1199.98 minus 1200 divided by 60.001 minus 60. And we get negative 20.0. So let's compare our slopes for our different intervals. For the biggest interval, we got negative 19.7. And then for the next smallest one, we got negative 19.9, then negative 20, negative 20, negative 20. So it seems like the smaller we get, we just kind of are stopped flat at that negative 20. It doesn't seem to change anymore. And in fact, I'll tell you, if we go one smaller, if we went to 0.0001 seconds past 60, we get the same thing. That seems to be our stopping point. So we can conclude with, therefore, the instantaneous rate of change, which I'm abbreviating to ROC, is negative 20.0 liters per minute. Sorry, I think I might have said seconds a couple times. It should be minutes. Okay. So now it's still a little bit kind of cobbling together a solution. It's not super accurate, but at least we're able to get something that's really representative of what's happening at that specific point in time. A real snapshot of how much water we're losing at 60 minutes exactly. So now that we've done that, now we can start talking about using a bit more elegant math to try and get this a little bit better. So to do that, let's talk about the slope formula, and we're going to see if we can figure things out a bit better. So the first section of this next part of the note is kind of our basic understanding of slope. We're taking 2 points, we're going to call them P and Q, represent them with A's and B's. So if we do that, the difference in the y's is going to be f of b minus f of a. The difference in the x's is b minus a, which we're representing in this formula up top. But we said that having the time interval is important because if we can control that, we can control how accurate our solution is going to be. So what I'm going to ask us to do is just kind of forget about that first bit for a little while, and we're just going to rethink it a little bit, and we're just going to reimagine this in terms of a time interval instead. So we're going to have this time interval h, and we're going to say, instead of doing a and b, we're going to keep a, but instead of b, we're going to take a and we're just going to add on the time interval. So let's think of the last problem where we had a would be 60 minutes, and our time interval will be 3 minutes ahead. So we're just going to take 60 plus 3, or 63. So a plus h is going to represent our second point. We're just taking our initial time that we're measuring, and we're going to just add on our time interval. And then for our y's, all we do is we're going to have f of a plus h, which is this one up here. This one down here is going to be f of a. So to find the difference in your y's, you're going to have f of a plus h minus f of a. So now, when we think of it like that, we get these 2 points, p and q, a and f of a, and a plus h, and a of f of a plus h. So to find the slope of the secant, we're just going to do what we usually do, y2 minus y1 over x2 minus x1. So that's going to be f of a plus h minus f of a minus x2, it would be in this case a plus h, and then we do minus x1 is a. But if you look at the bottom of this fraction, you notice we have an a and a minus a, so that can just be h. And the top stays the same. So really, when we're talking about a time interval, all we have to do is subtract our y's and then divide over the time interval. And that's going to tell us exactly what our rate of change is over that interval. So now that we know that, the big problem with finding instantaneous rate of change is that we'd have to have a time interval of 0, going from 60 to 60 instead. So the time interval would have to be 0, and we know we can't do that at this point. So that's not super helpful just yet. So trying to plug numbers in just as this is not going to work. But the trick is that we don't have to actually just stick with numbers for this. We can actually use whole equations, which we're going to deal with right now. Just remember, when we talk about f, it's a function. So we can actually put whole functions in there. So to start figuring that out, let's use an example to help us. So you are cleaning the outside of the patio at an apartment, which is located about 90 meters above the ground. You accidentally kick a flower pot over the edge of the balcony. The height of the falling object can be modeled by s of t equals 90 minus 4.9 t squared. It asks us in part A to find an algebraic expression to represent the average rate of change of the height above the ground of the falling flower pot. Simplify your expression. So first thing I want to point out, when you see the expression average rate of change, always think slope of the secant. Remember, rate of change always means slope, and average rate of change means the slope of the secant. So before we do anything, we're going to think slope of secant. So to start us off, I've written out that slope of a secant formula that we just found up above. So we're going to try to use this to help us out this time. So the trouble is that we're not thinking in terms of F's and A's and H's. So instead of doing that, what we're going to do is we're going to rewrite this just a bit. So we're going to say, we're going to call this, we're not working with F of A, we're working at S of T. So we're going to think S of T, and the first part of this is going to be S of T minus H. So thinking in S's and T's, this is what it would look like. So H always stays the same, but your function, the letter for your function and your variable are going to change based on the problem. So in this case, sorry, that should be T plus H. So in this case, all we're going to do is we're going to figure out our functions S of T plus H and S of T. S of T we just said is 90 minus 4.9 T squared. And for S of T plus H, all we're going to do is we're going to take that S of T formula, and every time we have a T, we're going to write in T plus H. We're going to sub that in. So 90 minus 4.9 T plus H squared. And as a good rule of thumb, I always put brackets around your T plus H. That way you remember that it all kind of fits together. So now that we've done that, let's plug that in. So S of T plus H we said was 90 minus 4.9 t plus h squared minus, I'll put this in brackets just so we know what to do with that minus properly. So 90 minus 4.9 t squared. That's all going to be over h. So at this point, this doesn't look super helpful, but let's see if we can simplify it, and maybe it will help us a bit. So let's start. Let's go left to right. So 90 minus 4.9. We have t plus h squared. We can use FOIL to help us riddle that out. So that's going to be t squared plus 2th plus h squared. Then we have brackets here. So let's take that minus out front and let's clean that up. So it becomes minus 90. And then we have a double negative, so it becomes plus 4.9 t squared all over h. Never forget your h at the bottom. Okay, next step, let's use distributive law and simplify the brackets in the middle. So 90 minus 4.9 t squared. That's going to be minus 4.9 times 2 is minus 9.8 th. Then we have minus 4.9 h squared minus 90 plus 4.9 t squared all over h. Okay, this looks a little easier to work with. We have some stuff that we can do here. So let's start by collecting our like terms. So we notice that we have 90 and minus 90, so they're going to cancel. And we have 4.9 t squared and minus 4.9 t squared, so they cancel. And now we have negative 4.9 h squared minus 9.8 th over h. And since we have h's and everything, we can cancel them out. So that becomes negative 4.9 times h minus 9.8 t. So now that we have that, now if we have our time that we're measuring from and we have a time interval, now we can use that to help us figure out some information. So part B is asking us to determine the average rate of change between 1 second and 3 seconds after it fell from the balcony. So we're going to use average rate of change. We just found a slope for the average rate of change, or a formula for the average rate of change, the last part, and that was negative 9.8 t minus 4.9 h. So we just need to know our starting time and our time interval. So if it's 1 second to 3 seconds, our starting time is going to be 1 second. And our interval over which we're measuring is the amount of time between 1 second to 3 seconds, which is 2 seconds. So now that we have that, we can plug those numbers in. We get negative 9.8 times 1 minus 4.9 times 2. That's going to be negative 9.8 minus 9.8, or negative 19.6 meters per second. So over those 2 seconds, between 1 and 3 seconds, the height of this flower pot is changing on average by negative 19.6 meters per second. So that's not super accurate, because we know that if we throw a flower pot off the balcony, the speed's going to change very quickly over 2 seconds. So let's get a little bit smaller. So let's start by looking at. Let's go with 3 seconds, and we're going to look 0.1 seconds ahead. So that's going to be between 3 to 3.01 seconds. For that one, the slope is going to be negative 9.8 times 3 minus 4.9 times 0.01. Just same formula that we found in part A. And if you do that correctly, you're going to get negative 29.649 meters per second. Second row is 3 seconds, and we're looking 0.001 seconds ahead, so it's 3 to 3.001 seconds. And that's going to be m equals negative 9.8 times 3 minus 4.9 times 0.001, and that becomes negative 29.6049 meters per second. I want you to compare. Look at the first row versus the second row. We have negative 29.649, and then we get negative 29.6049. So hopefully you notice that 4 and the 9, they shifted over by a digit. So it makes sense that would probably shift over again, but let's confirm. So negative 9.8 times 3 minus 4.9 times 0.0001. And you plug that in, it becomes negative 29.60049 meters per second. So what happens is, as you make that interval smaller, as we get closer to 0, that 4 and the 9 shift over, and eventually we end up with negative 29.6 meters per second. Before we leave this, there's one more thing I want to point out to you really quickly. I want to add one more column to this. Let's say 3. And this time, we're going to add a 0. Now we said we can't divide by 0, so it creates a lot of problems. But you notice when we went from having this formula here where we had to divide by h, so we couldn't divide by 0. But we used a bit of math, and we managed to get rid of that 0 out of the denominator, and we got negative 4.9h plus or minus 9.8t. So now that actually eliminates the problem. So we've actually managed to work around the problem of not being able to divide by 0. So congratulations, we've now kind of beaten one of those fundamental laws of mathematics that really limits what we're able to do. So now that we've done that, let's take m equals negative 9.8 times 3 minus 4.9 times 0. And of course, negative 4.9 times 0 cancels, so we're left with negative 9.8 times 3, which is just negative 29.6 meters per second. So not only have we been able to estimate the instantaneous rate of change, we've actually been able to calculate it definitively. So therefore, the instantaneous rate of change is negative 29.6 meters per second. So now that we've done that, we basically had the building blocks of calculus. Calculus is all about trying to figure out rates of change, especially the part of calculus that we're going to deal with in this course. Over the next couple lessons, we're going to start talking about something called limits, and we're going to use a bit of extra knowledge to help make our solutions a bit more elegant and make the math a little bit more proper, so that way we really have a totally solid understanding of it. And then once we have that, then we can really start going to calculus and using it for more practical stuff. So for now, make sure, do a bit of practice with this stuff, and then we'll come back and start looking at limits in the next lesson. Thank you, everyone. Have a great rest of your day.